Hello everyone. Today, Omid and I, we are going to have a presentation about the current project that we are working on Redispace, and we are as a MLA. And I have a master's in software engineering from Ontario Tech University. And
Hi everyone, I'm also Omid. I'm also an MLA at Redispace. I've got my Master of Applied Science in Electrical and Computer Engineering from U of T. I'm mostly interested in multimodal LLMs and how we can use like audio and image processing to make them go further. Yeah.
So our project is enhancing automatic speech recognition accuracy by utilizing large language models for error correction. And we will have first an introduction and problem statement, and we will continue with the methodology, and then we will have the dataset overview. Then we will show the experiments and the results that we have gotten from these experiments. And also we finish with the conclusion and some suggestions for the future steps for the company. So what is the problem? So first we have to explain what is automatic speech recognition. So it is a technology that converts the spoken language into written text by analyzing and interpreting audio signals. These automatic speech recognition, they are mostly a speech-to-text model, and they have been trained on a very clear data set that they are pair of speech and transcript. So the thing is that we are using this ASR system in real-world applications. And real-world applications, the speech are prone to the noise, like people speak with different accents. And these models, they have not been trained on uncommon phrases as idiom and idioms. So they might generate some errors, like they may generate hallucinations, they might have repetitions, and also they may generate the homophones. Like the good example is here is a polar bear, that you speak about a polar bear, but your speech-to-text model, which is mostly the Whisper, that is from OpenAI, they might generate the solar bear. That is completely like unrelated. Or they might have errors in generating the correct name entities and number and dates. And yeah. So what is the motivation to like enhance these enhance these ASR systems? The thing is that in the company that we are working, they have a dubbing system named Mockingbird. They are trying to like convert the contents from like English to Spanish or any other language. So this ASR system is the main component of these systems. And as you can see, like if we have like errors within these systems, like if your ASR system generates some errors and generates some erroneous transcript, it might go down into your pipeline, and then you will have the wrong translation, and like it will completely cause a problem for the company, especially for their reputations, or they might cause extra cost and time for them to correct these erroneous transcripts. And the current solution for the company is that right now they are using human in the loop as a correction method for these type of errors. However, we came to the conclusion that we could automate this. We could like reduce the number of the people, the time and the cost by incorporating a large language model. The thing is that large language modules, since they have been trained on so many like enormous and huge amount of the corpus text, and they have seen like so many like information on different domains and areas, they are able to do this correction like as efficient as the human or even better than them.
So our objective becomes like how to incorporate an external LLM as a post-processing module for these ASR outputs. The aim and the goal behind that is that, like as Sevda mentioned, these LLMs leverage the contextual understanding that they have learned from like large-scale training data. So our solution would look like something like this. The audio would go through the ASR module, which in our case, it's the OpenAI Whisper. So it goes through that. It generates multiple hypotheses. What it thinks like the highest probability of the outputs, what it thinks like the transcripts should be. So we choose like the top, for example, 5 of those hypotheses. It looks like something like this. So they're different in some words. So it's a variety of the tokens that are the highest probability in that sense. So these would be like the input to the external LLM. And we expect the LLM to use like all of the tokens here, like the context of the text, and then hopefully get to the target, which is like the correct version, which is either one of these hypotheses or a mixture of them. The reason that we chose like this type of approach was that we did like tons of literature review, and like we figured that prompt engineering specifically works really well for the ASR correction task. The reason being that it works really well without training data, and also it works well with limited resources. So in order to do that, we started in like simple steps. So we started with zero shot. For zero shot, we let me speak to like 3 settings of how we can apply that. The easiest would be to the constraint, which is just selecting the best correction from the hypotheses, like asking the LLM to do that. The unconstrained would be like model freely generating whatever correction it seems right. And also closest would be using this unconstrained approach and then choosing the closest one in those hypotheses. And like the instruction that the prompt that would be given to the LLM would look like something like this. It starts with defining the role, the correction rules, and also if it's, for example, in a few shot setting, it has these like in context examples, and then like giving out the hypothesis at the end. We can like even move it like one step forward, so we can like make it into like different steps. So like initially asking to detect the potential error, detect like the erroneous words, and then asking for like the error correction of final one. So we came up with this approach because we tried other approaches like chain of thought or task activating, which we'll talk more in detail experiments. To evaluate the approaches, we used word error reduction. It was like our main metric. In order to like explain it, I first need to like categorize errors. So we can categorize errors into 3 groups of insertion, substitution, and deletion, which are shown here. I think they are like pretty obvious, but like it's just like insertion would be just adding some hallucination, some random word. Substitution just like changing the word, and like deletion not including it. So the word error rate would be the sum of these errors divided by the number of words in the reference target. And we often show the results on the percentage of improvement for this metric. We also use some supporting metrics such as like METEOR to check the context and like the semantics, and also how we can reduce the human annotation time. To do the experiments, we use like a variety of data sets. So for each data that we are using, we need the reference transcript, which is our target, and like the 5 top hypotheses that the Whisper generates. And like for the actual data, we use like 2 open source models, the HyPoraidse and the GigaSpeech. For the HyPoraidse, we chose 3 subsets of common voice, LRS, and chime. Like the first one being like the different accents of English, the second one being documentaries, BBC documentaries, and like the third one being like noisy environments. And like we also used some entertainment set from GigaSpeech, which is like YouTube audio, to have like a variety of data. And for pre-processing, we just try to standardize things by lowercasing and removing punctuation, and also like filtering out short transcripts. We initially did some sort of model exploration to see how different models perform. We check like different open source models, like the LLaMA versions, the Mistral, Gemma, and also like the DeepSeek reasoning models. And we also tried the non-free GPT-4o and GPT-4o mini to see what's like the best available approach. Our results show that while some like open source models perform really well, specifically like Gemma was performing really well, but just like 9 billion parameters, still the best results were being done by like the GPT-4o. So at the end, like we chose these 3 models because like they were performing really well, and one of them is like the state of the art, the other is like a bit cheaper but still good, and like the other one, the Gemma, is like the open source one. We followed that with experiments on like different methods that we could use. So for common voice data, with these 3 models, we did like a variety of like different approaches that we mentioned, like different settings of zero shot, different settings of few shot. We did hyperparameter tuning. We did like different prompting and instructions for each one. At the end, like we saw like significant improvements in word error reduction, almost like 90% on this data, and the other data sets followed as well. For the like short time that we have, we won't go through them, but like we saw the same pattern in all of them. We also figured that like the best performing approach changes based on the size of the model. So for 4o, the best is coming with the unconstrained, allowing it to do whatever it wants. That's not the same with the other ones, meaning that like they are better when they're limited. Finally, we did some also exploratory data analysis on the errors. So how does error correction affect the distribution of these errors? So like the word error rate, which is like all of the errors, could be categorized into these three, as mentioned before. In all of the areas after error correction, we are seeing improvement. We are just seeing like increase in the deletion. That's like the only one which is increasing, which shows that like when we are allowing LLM to do error correction, it is like removing some words which things are like not relevant. So we have to keep that in mind.
So what is our conclusion and suggestion as a future step for the company? So in conclusion, we conduct experiments with 3 datasets as a main ones, and we have improvement regarding the word error rate reductions for common voice up to almost 90%, and for LRS and chime up to 30%, while not only preserving the METEOR metric, but also improving it at the same time. So it was a great achievement, considering the only prompt tuning and prompt engineering, and how other methods, for example, fine tuning or these kind of methods are costly and time consuming. So considering that our method was able to be effective in comparison to other methods, and we calculated the impact of these methods on the company's cost. We noticed that we are able to improve the dubbing quality, and we can reduce the human annotation cost by up to 50%. And also we noticed that how prompt tuning and showing the good examples for these large language models can be effective and perform at the same level of as I said, costly methods such as fine tuning or any other methods. And also we based on the experiments that we we noticed that methods, for example, methods such as chain of thought and text activation, they are not performing for error correction for the ASR systems. So we skip completely the models such as DeepSeek, and we noticed that they are not good for this kind of tasks. And also, as a suggestion for the next step, for this, we did a comprehensive error analysis for the data that they were not showing good improvement based on the incorporating large language models. We noticed that these kind of errors, they are related to the numbers and also acronyms. For example, they are not able to detect that MCI is MCI. They only generated on the character N. So for this kind of errors, we are proposing and we are suggesting to use the more to add extra contextual information. For example, applying the RAG application or providing longer transcripts for these large language models. And the other approach could be using the acoustic features beside the transcript and text features to the large language model. And the next step that we are going to do, we are going to do the whole experiments and repeat this pipeline for the Red Spaces client data and analyze them at the same way that they previously did for the previous data set that we talked about.
Thanks very much.
Just for confirmation's sake, the hypotheses are generated by Whisper or?
It's Whisper large. So there are different tiers of Whisper. So if you use the lower tier, for example, Whisper tiny, there are tons of more errors to be reduced. Whisper large is achieving really good results by itself. So this is pushing it to the probably the state of the art that we could get with the prompt engineering, because clients want almost 100% accuracy.
In your experiment, just you can say for the curiosity's sake, how much is the difference? So for example, if we just want to, you can say, utilize the lower rank Whisper, not the top tier one, what was the, you can say, in and all, you can say your metrics wise, it was dropping a lot. So every time it was selecting the hypothesis that was pertaining to, you can say, the stronger Whisper model, or it was choosing the weaker one as well.
So the way it works is that, for example, company uses a version, for example, the large one. So what they are doing right now, they are just using the top hypothesis, just selecting that, and then sending it to someone to fix an error that he hears from, he or she hears from the audio. So if we use lower versions, that one would be higher in error. it would be much more. So for example, one of our data sets, like the entertainment data, that's from the Mr. Tiny. We see much more improvements in those ones actually, because it is much more erroneous, but it is not what our company is using. So we went with the more complex case.
Thank you.